Hey everybody, Dave Lindberg in Hong Kong with another episode of the THD Podcast. Today we have a special DSP company joining us from Sweden named Dirac. But without delay, we must make sure that we mention that we are sponsored by the ALTI Association. So we encourage everybody to go out and get involved with their networking organization and find out all the benefits of being a member with ALTI. So let's quickly move into meeting everybody. As always, Simon from Japan. How are you doing today, Simon?
Good, Dave.
Good day. You're quite dark today. I hope that reflects your mood. Does that mean there's going to be a lot of tough questions?
No, but it's like you said, I'm sitting around the campfire, so it's
Okay.
firelight.
Okay. So yeah, joining us from Stockholm is Mathias Johansson, the Chief Product Officer with Dirac. And so Dirac is a world-known audio technology company, and they're on a mission to invent the future of sound. So they specialize in digital audio optimization, which my interpretation is that's some DSP technology. So are we on the right track, Mathias?
Perfectly on track. Yes, that's what we love and indulge in on a daily basis. Yes.
Okay.
Nice to be here, by the way. Thank you.
Yeah, no, thank you for joining us. So it looks like Dirac covers a lot of different market spaces for audio. I see headphones, I see automotive, I see some studio and pro on your website. So maybe you can tell us a bit about. I noticed a lot in headphones is what I've noticed recently, making the news. So where would you like to start in introducing the company, I guess?
Yeah, that's right. I mean, we are really, what we're trying to do is create superior sound experience by use of software and algorithms for really any type of form factor, for any type of device type. Everything from, like you mentioned, headphones, smartphones. We're probably mostly known for home theater systems with room correction and maybe car audio. But we're really sort of all over the place in that respect, because we have developed a set of fundamental technologies that really solve a lot of the acoustical problems and challenges, regardless of your form factor. And then certain things are specialized. So I was thinking today of actually going through a bit of those in fairly technical detail from market to market a bit, because there are differences, obviously. So perhaps I should share my presentation.
Sure, that'd be great.
Here we go. So as I said, first of all, I'd like to introduce a little bit about the company itself and what we call our audio platform, because it really is a platform of different technologies for various use cases that we then use and apply on various markets, such as automotive, home and pro, headphones, mobiles and PC, and more. So I'll just jump into it, and feel free to ask questions anytime.
Okay.
And the way we look at ourselves, we like to think we are pioneers in this field of digital signal processing for audio. We actually started. I was one of the founders. I did a master thesis once upon a time, more than 20 years ago, on how to improve small speakers with the help of signal processing. And since then we founded the company then in 2001, and it's been a fun ride to see how the industry has evolved and are now embracing digital technology, which wasn't the case back in 2000. And there were real reasons for that, of course. You didn't have processing power. And to be honest, a lot of the stuff that was done digitally wasn't maybe in order to really optimize and create a better sound experience. And we look at ourselves as optimizing hardware to create the best possible sound experience. We're not about, let's say, gimmicks and sound effects so much. It's more about picking a physical hardware to its limitations and creating the best possible experience from that. So we like to, the combination of really advanced mathematics and signal processing, getting it to work in a small form factor, battery limited, MIPS memory limited, but still getting a really superior, surprising sound experience. That's what we always strive for, a surprising sound experience. So the whole idea is to upgrade your hardware without actually needing to change the hardware and get the best possible sound out of it.
And your I read your namesake. Your company's named after Paul Dirac. So is that because somebody inventing the algorithm was a fan of his equation, or you actually maybe leveraged some of that in your algorithm?
You're definitely on to the start of the company. It was funny because we had a different name for the company first when we sort of were envisioning starting the company, but it turned out that name was taken. And then we started thinking about what is it we're really doing. And what was unique when we started the company, and to some extent is even today actually, was our time domain correction. We were pretty good at robustly improving and optimizing impulse responses. And we said, if a speaker system manages to have a perfect impulse response, which is characterized by a perfect Dirac impulse, right? Then we have achieved sort of perfection, at least theoretically. So that was actually the background of choosing that name.
Okay, cool. Famous name.
Yep. And then we went into different areas step by step. We started out in automotive. BMW was our first customer. And that was back in 2004. We started working with them. The reason why they were quick to adopt advanced digital signal processing was that they had a very high ambitions with their sound systems in their cars. Were very visionary, and they had real problems. You know how it is in a car cabin. It's extremely challenging acoustically. And at the same time, even in those days, they had DSPs. They were using, I think, Shark DSPs actually already then. Right. So there was some processing power, and there was a real problem. All these early reflections, the standing waves, the speaker placements, those things were really hard for anybody to get a grip on. And we managed to find ways to reduce those early reflections a lot and even out both the spectral response, but also in the time domain, make a much better direct wave. And that created the company in a sense, because that has been the basis also for our room correction in the home audio markets and so on. And I'll get back a little bit to those technical details. But from the automotive industry, we went then into sort of home cinema and studios and professional cinemas with room correction technology, and on to other form factors like mobile devices, headphones, small speakers. But you could sort of to group our different technologies. One is what we call upgraded performance, simply more like a factory calibration, using our technologies, algorithms, and a tuning tool. You're helped as a sound engineer to achieve the best possible sound experience. And I'll get back to that a little bit more, the different technologies in that. And then the other part that is very popular these days, of course, is immersive audio, spatial audio. So various technologies to take a form factor such as a smartphone, for example, to sound bigger than it is, to get sound moving outside of the physical confines of that device, but doing it in a robust way and in a way that sounds good and not just like something you get a headache from, of course. So we've a big portfolio in that space, so to speak. And then, of course, the third part is adaptive and intelligent technologies that adapt either to content or to context, like room correction, those kind of technologies that adapt to things. And generally, we are measurement-based, optimization-based. We measure acoustically a device in many positions, get like a full acoustic fingerprint, and then use different types of algorithms to improve the sound overall. Okay. And some of the form factors and some of the companies we've been fortunate enough to work with are here, like the Bowers & Wilkins and Harman Kardon systems at Volvo. We work a lot with Harman on the automotive side and also on the home audio side. And in a very different form factor, right, the ROG Phone 5 from Asus, which is a really nice sounding phone. You would think small mobile phones can't really reproduce sound very well, but I think this one takes a step above the standards of that industry, really, by employing the very latest in signal processing, and of course also getting better and better in the speaker arena as well. Because the micro speakers are constantly being pushed. We were working very closely with AAC for many years, right. and together we're of course trying to push the boundaries of what these tiny form factors can do. as well as Klipsch TWS earphones that are the latest area, which is of course booming a lot right now. And on the room or home audio side, room correction has become very important to us and to general users. It's now a sort of a must-have for a serious AVR to have, and NAD is one of our customers. Mm-hmm. And even what's happening in the hi-fi industry is that we're not just seeing the sort of the typical hi-fi brands being branding partners for automotive sound systems. Actually, BYD in their Han model, which is a great electric vehicle, came out last summer. They're using us also as a branding partner. So we're helping design the whole sound system. So it shifts sort of the value from the hardware to the software. And the hardware is, of course, necessary. We cannot break the laws of physics. But when you design jointly, when you understand what the DSP algorithms can do and what they cannot do, and likewise with the analog part, with the mechanical parts, then you can design a system that is really much better than if you first design your hardware sound system independently and then apply signal processing afterwards. Right. So this is a philosophy we have, and we really think the industry should think more about this. I think there's lots to gain there still.
Yeah, I think that's a universal engineering issue, whether it's signal correction, is they build the system and they bring you the problem, Dirac, or in another solution, maybe it's a mechanical issue and they design it and they build it and then they go to a mechanical engineer and say, well, it doesn't quite fit in the door of the car. So it's kind of it's a common theme, it seems.
Absolutely. I mean, if you're able to take the system approach and combine all the competences in one place in the early design phase, you can achieve much better results. But on the other hand, it is highly complex because there are so many different knowledge domains that need to be included to do that. So it is understandable as we end up in these kind of situations still today.
Do you get involved in helping with like proof of concept? You said you worked with AAC. Yes. Do you do some proof of concept speaker designs, and you have some mechanical acoustic guys in Sweden to help develop it for the customers?
Absolutely, yeah. The earlier we can come in, the better, we think, because then we can also affect, especially if you're talking about now, you're getting more and more speaker systems that have more than one speaker or two speakers for array processing and stuff. We've done a lot of prototypes, proof of concepts together with customers on creating, say, immersive sound experience for smaller form factors, like a little sound bar for your TV or even for your PC and so on. And then, just where you place the speakers create a very different playground for the algorithms to create the most diversity out of that system and so on. And sometimes we've actually gone so far as to really, together with the customer, create new drivers together with the driver manufacturer. And that's been on occasion, we would like that to happen more often, actually, to really create sort of new designs. So that happens quite a bit, actually. Not all the time, but quite a bit.
Okay.
And so what we've done here, if you look at this screen, is we've created by now a platform of different DSP technologies. A lot of it is fundamentally the same components that we reuse. The stuff we developed together with BMW, actually, for multi-channel processing and multi-speaker arrays is something we did more than 10 years ago, and we're now applying those things in mobile phones with, of course, slightly different constraints, right, on the speakers and so on, but still based on the same fundamental principles of co-optimizing several speakers to reach a certain target sound field. And that's really a theme that's recurring for us. We also, it goes the other way around, but especially in the automotive scene, it's interesting now where there's so many things happening, right? That you're with the electric vehicles, the power consumption and so on. There's a lot of focus on being able to reduce the weight, maybe using even micro speakers in cars. And then, of course, the mobile technology we've developed for the small speakers that are about extending the bass, increasing loudness, preventing distortion, and so on, all of a sudden become very important for the automotive space. So we see a lot of synergies, and that's why we are in those different fields actually, because we reuse and we see how these different markets are converging in many senses actually. And we've combined that lately in the last few years really into one platform. And it's all about getting a superior experience in the end, sound quality, objectively and subjectively. But also for an OEM, to get more consistent sound. If I am a car producer, for example, I want to have a consistent sound experience, let's say a BMW sound experience. And to achieve that with different hardware components is a challenging task. And it means you need this kind of algorithms to make it sound similar. And also across different device categories. There are more and more companies that are even branching out, even from automotive to other areas and vice versa. We're hearing Xiaomi, that's a mobile phone company, you might say, well, they're branching out into automotive as well, right? And to get consistent sort of branded sound signatures across device categories is a big thing, while also saving time. And that's part of the lower cost here, right? That we have this tuning tool, because tuning a sound system, especially in cars, but also elsewhere, takes a lot of time and it's hard. And therefore, we've taken this approach we call assisted tuning. So it's more like you get a toolbox from us and you can do your job faster and better. You get more flexibility in your tool set. And of course, the really nasty part about being in the DSP business is that you need to integrate on all these different platforms. And of course, being in all these different areas where we are now, we have been able and had to, implement those advanced technologies onto, everything from Bluetooth chipsets to mobile phone chipsets to home audio, DSPs, ARMs, et cetera. And that's becoming, of course, a big asset as well, the simple fact that we have those integrations. But in essence, it's a kind of an all-in-one platform for optimizing sound across different device categories.
Okay.
And maybe let's get a little bit more technical and go into the automotive side. As I said, what we're doing here and elsewhere really is built upon the synergies that we have across industries, and it's most prevalent right now in the automotive industry, I would say, where we're getting a lot of requests also now for new types of speaker layouts, for example. And of course, if cars become self-driving, the use case becomes very different. You have to be able to control the sound, optimize the sound for new type of arrangements inside the car, etc. So the job here is, again, to deliver superior sound in every seat, faster, easier, and consistently. And it's really from measurement. So what we provide to our customers is a measurement tool or a measurement and tuning tool that takes you all the way from the measurement. And it's a whole measurement procedure, in fact, to get the good acoustical fingerprint from the car onto integration into the amplifier in the car or head unit. And as I said, we call this assisted tuning. So it really empowers the sound engineer to get full control over the end result. And in-car experiences are also getting more and more diverse. Now with the COVID situation, a lot of talk right now about conferencing in cars, etc., getting more traction. You are often driving and having conversations. It's still so in terms of the experience. And of course 3D audio becoming important as well. So we have gone from having this impulse response, frequency response correction that we first did for BMW to a full set of, a full signal chain for those different use cases, taking care of problems such as center images. I'll get back to these things, and of course enlarging the space that you're in, because that's one of the problems in the car, the confined space you're in. And now we're seeing also applications of spatial audio coming into automotive as well. and head tracking and so on actually starting to at least be on say prototype levels, not so much commercially available yet though. So the way we've packaged our different automotive technologies is to help our OEM customers is to have actually 3 levels of packages, and then you can of course also use add-ons and so on to achieve what you like. But in essence, you have a performance package that's primarily intended for standard sound systems. Really fast process to get to a good sound for both the background and foreground tunings, and then up to the premium level, which typically is applied to branded sound systems, and then up to the professional level, which is the highest sound system levels. A lot of the car manufacturers, of course, have 3 tiers themselves, and so this is done to sort of match their tiering.
Right.
And one of the things, now getting a little bit more technical, that's necessary in cars, of course, is target sound management. So this is included in this performance package. You have a target sound signature that you want to achieve in your car, and we optimize your biquad filters, which you typically would have in your standard car system. You wouldn't have more advanced filter types to achieve that on average throughout the car. And we're looking, of course, both at acoustically, but also we have to look at psychoacoustically how to set the biquad coefficients in the right way when you're confined. Let's say you only have 5 biquads per channel. Well, then you have to make compromises. You cannot fix everything in a magnitude response. But what are the most important things? Well, that's where the psychoacoustics come into our criteria, our optimization criteria. And of course, the other thing is you still have at least 4 channels, even in entry-level cars. So you need to look at the sum responses and making sure that they add up nicely, coherently. And what another big issue, of course, in cars is that you have typically a left and a right speaker, but not a center speaker in your entry-level system. So you get near side bias. And also you get an asymmetrical stage, but the main problem is maybe the near side bias, that kind of all sound collapses to your left side if you're sitting on the left side.
Yeah.
And then what we have done is we've developed, since we anyway measure, that's the first step in a car, you measure the whole sound system with a microphone array that you put in the different seats. Based on those, we can of course see how the different speakers then add up at the various positions, the left and the right positions here. And then we can look at, what would happen if you actually had a center speaker, a physical speaker? How would they add up then? And based on all pass filters on the left and the right channels, we can create an illusion or a similar experience as if you had one there, where the 2 speakers actually sum up coherently both here and there. And that has a great effect, not just that the center image stabilizes, but normally what you get with this interference is also the comp filtering, so you get suck outs, and we remove that as well. So you also get the neater sum response.
Just before I forget that, you mentioned that you use an all-pass filter. That changes phase as a function of frequency. Is that what you're doing?
Exactly.
And
so at various frequencies, we adjust the phase. So the idea is that you have more or less out of phase behavior at certain frequencies, and by adjusting the phase of one of the channels at that frequency, you can make them sound more in phase, so to speak.
Right. Yeah.
Not
So
always perfect phase.
You're not always perfectly, but you're in a simplified fashion. You're looking at the distance between the speakers and the listener's head and trying to find more or less an optimum phase that will line up more or less the whole frequency range.
Exactly. And the thing is that and if you didn't have the room acoustics, actually all you would need to have is the distance. But the room acoustics in cars are terrible, and with all those reflections going on, it's not sufficient to just have the distance. You really need to measure the whole transfer functions to really measure what happens when you sum up all these additional secondary paths as well that you get. That's precisely the idea.
Okay.
And also for sort of entry-level systems, there's a big demand to also have some form of surround experience, nevertheless, from 2-channel input material. And so what we've done is we've developed a rather simple upmixing algorithm, but because it needs to be simple to fit in the entry-level DSPs, but using sort of an intelligent mix of gains, delays, and phase controls, we can achieve something which is very robust and creates actually a pretty nice surround experience in just a 4-channel car. So that's something you can do to really improve the sound in the entry-level systems. One of the things, of course, is the entry-level systems don't have subwoofers. So what to do with the bass response? Also, another problem is that you often get rattling and door buzz and all those things in the bass region, so you cannot push the bass too much. And then what we thought would be a nice thing is to add virtual bass techniques that are common in improving microspeaker performance. So what you do there is you're adding harmonics to sort of trick your brain into thinking that there's a fundamental frequency as well down there at, say, 100 hertz or 80 hertz, but you're really just adding the right harmonics to trick the brain into thinking that. And if done right, it gives a nice bass experience, actually. And it has another benefit, and that is, of course, that it doesn't draw a lot of current as it would do to have a bigger woofer. And you avoid rattling in the door. So it's actually quite powerful. There's limits to what you can do, of course, with this virtual bass, but it's actually a very useful technique, especially for these entry-level cars.
Right.
And then if we go to what I personally like the most is the higher segments where you can really achieve sort of perfection. And what we sold to BMW back in the day is still being used in lots of premium cars that we work with. And that's what we call Dirac Live, which is frequency response correction and impulse response correction. And when we talk about, and this, by the way, if this is actually pictures from a home rather than a car, the impulse responses in cars look way nastier, but it's the same principle. The difficulty of achieving high quality sound in a car, I would say, isn't primarily the standing waves. It is truly the early reflections. Even if let's say you have a center speaker, which a lot of premium systems have, you don't typically get a direct line of sight to the speaker. So what you're hearing is the reflection off of the windshield, and then a lot of reflections. So it's really messed up. And if you think about that, what really makes it sound worse when you have all these early reflections is the fact that you have multiple speakers with different reverberation patterns or early reflection patterns from each one of them. So what happens is that the stereo image or the stereo information is lost because all the correlation between the left and the right channel that was on my recording goes through that system, and with those reflections adds up completely randomly in phase, you could say. So and all these correlations between left and right ears, that's how we determine where is a sound source localized. And that's what you hear in a lot of car sound systems. When you listen to voices, for example, it's hard to pinpoint. The voice typically gets smeared out and gets very broad. Certain frequencies are over here, others are here, hard to localize. And that actually creates a lot of listening fatigue. And when you can, with this mixed phase impulse response control, we're able to figure out sort of the common denominators in the impulse response and these early reflection patterns. And we can reduce the early reflections. We cannot remove them, that's impossible. But we can make the direct wave, or the ratio between the direct wave to the reverberation to be much bigger.
Yes.
So that the direct wave becomes more dominant. That helps in staging tremendously, which to me is a huge difference in terms of perceived sound quality. And that's one of the main differences you get when you actually do the impulse response control and not just the magnitude response.
Yep.
Okay.
And then we go to what we call the professional level. And let's maybe skip the detailed page here. But if we look at one of the core technologies there that I think is really interesting is a MIMO mixed phase correction. And what is that? So we had this impulse response correction that I just talked about. And some 15 years ago or something, we started thinking about how can we generalize that to multiple speakers. In a car, in a premium car, we have sometimes 20 speakers and more at the same time. What if we could combine them together to actually reduce all these reflections? Think of it almost like an active noise control system, that one speaker is playing the primary signal, and then other speakers are sort of sending out anti-signals that take away the undesired reflections from various locations, from various walls and so on. And that led eventually to this technique that we've also called at times Dirac unison. MIMO stands for multiple input, multiple output correction, where they're using all of the speakers, or at least several speakers, it depends, together to create sort of a super speaker, to create an active room treatment. So because if you think about it, of course, I can maybe adjust with one speaker, I can adjust the early reflections coming from the same direction as that speaker, but I cannot do anything about sort of reflections coming from another direction unless I have a speaker from that other direction. Then that can go in and help reduce those reflections. It's a highly complex optimization problem. But in the end, what we managed to do is, if you look at this picture up to the left here, this is a frequency response, the magnitude response, measured in, I think, 64 microphone positions. And you see an average response and then the individual variations, huge variations. But after we've used this technique to use the speaker, in this case, I think it is 14 speakers together.
Yeah.
Then we even out the average response, but also the variations. So it means that you no longer have a peak at, say, 100 hertz in the front seat and a dip at the same frequency in the back seat. You get a flat response.
Okay. So if I could try to summarize this down, so you're measuring with, say, inside a car or inside a room, you're measuring with 64 microphone positions, and then you're running your algorithm to adjust for each of the deficiencies, perhaps, let's say, with reflection or phase or other issues, to make sure that overall the whole sound throughout those 64 mic positions are as close to flat or as close to what you want for a frequency response. So it's the sum of, okay.
You're not just looking at an average, you're actually looking at each of these measurement points.
Right.
And you're using all the speakers to control them together. It's like you're standing in a wave field, and at all sides of the wave field, you're holding something to control the waves in the middle. And then you can make this wave field completely flat in that region. In a sense.
Right. And so that's really becoming possible because of the horsepower available in relatively low-cost signal process or microcontroller DSPs. Yeah. Okay. Sorry, Simon. Go ahead.
No, the gray curves are the individual responses from 64 microphones.
Yes, exactly.
So by the time you get up to say 1 or 2 kilohertz, it's very hard to do much around there, but it's incredibly powerful in the low frequencies.
Yep.
Is that dimensions of the car wavelength related?
Exactly. So the higher up in frequency you go, the wavelengths get smaller and it gets more and more chaotic. So you cannot control it to that extent. And that's the trick also, to realize that you cannot do that and not even try to do that. And to be, with the wavelength so short, just the fact that you have 2 ears and move about a bit, we're not really so sensitive to these tiny differences unless you're listening to a sinus, but that's rarely the case, not just a tone. So whereas in the bass, these differences can be quite big actually. And what we feel, and when you listen to this, when you have minimized the variations, it is also the fact that you're feeling like the bass is stronger and punchier. It's much drier. And that also is showing up in these pictures here in the lower part of the figure, this is what we call a waterfall plot or a spectral decay plot. So you have the same frequency response here, and then you have a time axis here, which is how these different frequencies decay over time when you just put in this impulse, this Dirac pulse into the system, look at it spectrally. So you have all these ridges and valleys here, which is completely typical and to be expected in a room for sure, but it's also undesirable. And what you can achieve then instead when we've done this co-optimization of all the speakers is that these decays in this region, again, up to say kilohertz or so, vanish. And you might say, okay, but it didn't vanish down here at the very low frequency. No, that's because at this point we had one subwoofer only that was able to go at that low.
Right.
Whereas in the higher frequencies, you cannot do much. What you can see is that the very, very early reflections from the same direction are actually a little bit lower here, which is still important, but not a big difference there.
Yeah.
Okay.
So this is a real measurement out of a car, and you've got the bass going down to 30 hertz. That must be shockingly powerful.
And this technique is used in a couple of cars, and it's at least official in Volvo's Bowers & Wilkins sound systems. Also, the new Genesis cars are also having this, and a few others. And you can feel it in the bass. It is an unusually punchy bass to be a car. Normally, you have very boomy bass in cars, and this is much drier, much more of a high-end, hi-fi kind of bass.
Yeah.
So this is pretty neat. And then, of course, like I said, 3D audio and creating a larger space is another of the really hot topics, obviously, in the car scene, has always been. And ever since we started working with BMW, they had the same question. Can we sort of create speakers outside of the windows? Transform us to another sort of listening room. And ever since then, we've worked and improved on those techniques, so that we have a set of technologies that work quite well actually to make a convincing illusion of being in a larger space. Volvo asked us to come up with to simulate the acoustics of the Gothenburg Concert Hall, which is famous for its acoustics actually, and we were a little bit skeptical about it because there's also a DSP footprint. Even though it's pretty good now, it's nevertheless a challenging task to try to reproduce a space of this size. So we used various kinds of sound field synthesis techniques actually to do this emulation or simulation. So first with this MIMO technology, we kind of erased the acoustics of the car, if you like, up to a certain frequency again. And then we imposed this on top. So we were in the Gothenburg Concert Hall and took hundreds and hundreds of measurements to get a footprint of that, and then try to reproduce that as properly as possible in the car. And we had the conductor of the orchestra come in and sign off on the car as well. That was quite a challenging project with all the DSP constraints you have as well. But it's now available in the car, so you can actually listen to it. And I think it makes a pretty good impression actually.
Does that work well for classical pieces, or does it translate if Paul Oakenfold or Metallica play with the orchestra as well?
I personally drive a Volvo with this system, so I tend to use what we call the studio setting because I like my sound really dry. But on classical music, I think it plays really well in this setting.
Right.
Whereas in my mind, I don't see a point of putting Metallica in this kind of space in the first place, and it becomes, not my cup of tea. Maybe I'm getting a call from Volvo now, but for other types of music, definitely.
Yeah, I hear that's how they're getting the kids out to the opera halls these days.
Yeah, maybe that's just, and they have this computer game music concerts as well. At least here in Sweden, they do.
Okay, cool.
Cool. Yep.
All right, let's continue.
I just wanted to touch on this as well, which is Again, using several speakers in the car. This is a big trend now. Can we get rid of the door speakers in the car? Can we have a small sound bar or a speaker array in the dashboard instead? And in fact, yes, you can. We've shown this together with Harman at CES, for example. I think this car here is the demo car we used, with a small array of speakers up in the dashboard and no other speakers except for, I think in that case, we used also a subwoofer for the bass. And so we combine with this, again, with this MIMO technique. It's extremely, broad in application. It can essentially combine any number of speakers, types of speakers, to achieve any kind of target sound. And here the idea was then to do crosstalk cancellation at the ears of the listeners, the driver and the passenger, and thereby then create an illusion of having speakers around you or to the left and the right. And this, of course, becomes a cost-efficient solution, and you don't need to package speakers indoors. You get away from a lot of problems. So this is an interesting solution as well. Mm-hmm. And if we then just quickly go through a little bit about the home audio side, where room correction is our main focus, Home and Pro. We work with a lot of different brands on that area. Again, using this impulse and frequency response correction. And as a user, you can adjust your target sound. So we suggest a target curve based on the measurements, but you're also free to adjust it completely to your taste. And you can create many playback modes. The user interface runs either on a PC or on a smartphone or a tablet, and it's very custom install friendly. We have ways to measure asynchronously, so you don't need to have a microphone wired, with a cable that's a kilometer long and so on. So all these things that make life for the custom installer a little bit easier, we've thought about, because a lot of our customers obviously are in that custom install space.
Right.
And recently we added something we call bass control, which essentially is an automatic bass management, but it also draws on these MIMO technologies to even out the sound in the listening space as well. So if you have multiple subwoofers, this technique integrates them seamlessly with the rest of your speakers, so to speak. So you don't need to do all of that work manually, which is quite difficult and time consuming. And this is very popular now. It is used a lot, content creators and of course home theater systems. So there's literally thousands of room measurements being done with the Dirac Live software every day, it's a growing user base, and we're adding a new feature every year to this package. And this is sort of a consumer software that we license to hardware manufacturers. So, but you as an end user download the app and can run the calibration yourself.
What are DAWs?
Oh, sorry, digital audio workstations. So if you're producing sound in say Logic or in Pro Tools or something like that. So right. This is especially for the content creators. We have different plugin solutions like VST plugins and so on. Mm-hmm. And then when it comes to the hardware manufacturers, we implement on their DSPs, and we have a collaboration where we provide an SDK to the customer, and we do integration onto the devices. Mm. And then headphone side and mobile side, to come near to the conclusion of this. Headphones is, of course, an area which has been seen a lot of change recently. 10 years ago, we didn't have digital headphones, essentially, and now all of them are almost. So, and that opens up possibilities for us, of course, to add our algorithms to and integrate them on the actual headphone chips. And there what we do is similar to other things. We optimize, and of course the measurement procedure is different when you measure headphones. We use various types of measurement, ear simulators and stuff to measure the responses there and optimize to a target response that can then be implemented on the typical DSPs used in Bluetooth chipsets. But also we've done a big amount of work on spatial audio and with HRTFs, the head-related transfer functions, to come up with what we think is more accurate localization for headphone audio when you want to simulate, for example, a 5.1 or 7.1 setup, or even with height speakers, etc. We felt we've been working with HRTFs for many years, but we felt that the available ones on the market or publicly available weren't. They had problems. We always strive for perfection, and we wanted them to color the sound less. We wanted them to be more applicable to more people, and preciser in terms of localization. So we tried to go really, to the bottom with this, and created a measurement system and measured HRTFs of a lot of people, literally hundreds of measurements on real people in our labs, and was based on having a head tracker and microphones in your ears, and then asking people to move your head in all the different directions, move around naturally, and see what happened. And then we learned, and then we tried to create a universal database of HRTFs that should work for anybody and have a minimum of coloration on the sound, because we think it's very important to have clean sound first of all, and then clear directions. And that's what we're now employing when we do various types of spatial audio implementations. And then also we had to work on reverberation, because the HRTFs give you the angle and the direction of arrival of sound, but the externalization from headphones requires good reverberation that doesn't create nasty comp filtering and so on. So we created also a 3D reverberation engine based on that. So what we're doing sometimes in headphones is the opposite of what we're doing in home audio, where we're correcting the room, taking away reflections. Here we're adding them back again. But the idea is, of course, to create sort of a virtual reference listening environment. And I've claimed once that, in principle, we should be able to create a better acoustic experience in headphones than in real rooms, a virtual hi-fi experience, because we can control fully how the reverberation looks when you have headphones, which you can never do in a real room.
Okay.
And one of the things, when you think about spatial audio, a lot of people think about 3D and gaming and so on. And yes, that's of course a really nice feature. But actually, I would claim that the real benefit is just for traditional stereo music listening. And the reason is that music has been mixed for speaker listening most of the time. And when you put on headphones, you no longer have any crossfeed from the right speaker to the left ear and vice versa. Mm-hmm. And if you listen to Beatles like I do quite often, that's horrible. It doesn't work. So you need to have some kind of crossfeed, and that's where I think actually spatial audio has a real application, and we're happy to work with some truly classical hi-fi brands on headphone sound to make more of a stereo sound that's better than both speakers and headphones, we think. And what we find is that when you listen to this for hours and hours, you don't get as tired as you normally do when you listen to headphones.
Right. Yeah, ear fatigue's a big thing, especially, I know, well, hi-fi could be one with the traditional stereo recordings, but also the amount of hours that people play with gaming headphones as well. I know people looking for optimum sound in that category. I remember 10 years ago, gaming headphones were the cheapest ones on the shelf, but now there's easily $300 plus headphones in a common shop. Yeah. So yeah,
the price of high-end gaming headphones is picking up a lot.
Yeah, truly.
And of course, the same thing has happened on the regular headphone side as well. I guess there's a market now for really high-end headphones that didn't exist years ago either. And of course, yes, we do employ this on gaming headphones. For example, Philips has a gaming headset that uses our HRTF technology and also our optimization technology. It's embedded on a Windows driver, and it creates a 5.1 or 7.1, a multi-channel experience simply. So gaming is of course picking up. And then the final part that I have in my presentation here is also the microspeaker part for mobile solutions, which is an interesting field because the microspeakers have very different problems than the bigger speakers, obviously. There it's still important to correct the magnitude response and so on, but of course the main problem is distortion, loudness, lack of bass, and then we're working with other technologies in that field also. So here it's really about overcoming the small form factors to enable both immersive and sort of high quality experience as well. And what we're now showing customers is that we can even achieve actually multi-channel, we can enable multi-channel experiences on 2-speaker devices, so that with a smartphone in your hands, gaming or watching a movie, you can actually have a full panoramic sound experience and use multi-channel content as well. But of course, voice, music, and plus gaming and movie remain important use cases for these small devices. And for us, we're combining both the speaker technologies and headphone technologies with for our customers in this arena, so that you can get a consistently good experience on both form factors. So right now there's a lot of talk about immersion in mobile and getting surround sound, and of course head-tracked spatial audio for earphones. And that was this work I talked about on the headphone slides about creating this HRTF database that of course led up to a headphone solution that also can use head tracking or without head tracking. And of course you can use head tracking for example with a PC or with a screen, so that when you move your head you still have your virtual sort of speakers connected to the screen and not moving with you. And that's the whole point of head tracking.
And could you do it the other way for like VR environments where you turn your head and the sound would change? Okay, yeah, cool.
Yeah, exactly. Yes, so that's we do that, and we actually have implemented this in some VR applications, which exactly has that. You have this like glasses on, and you move around in your world, and you really have the full sound experience. And that was one of the things that led up to the work on HRTFs as well, that we thought VR and AR in particular was coming along quite fine in some sense. It's maybe not mass market adoption yet, but experiences were getting better and better. But the whole illusion completely broke down because audio was not at all following the visuals. It was still just sort of stereo audio. So that was one of the reasons why we thought, hey, we got to do something better here. And what we've done in one of our demos is, like what I talked about before, actually simulate in VR a perfect listening environment with a high-end speaker setup and so on, where you can watch movies and so on. So we did that as a little fun demo for customers. But we think that AR use cases are maybe the more interesting ones, or more mass market ones in a sense, because of course with VR you get completely occluded from the reality around you, which limits the use cases. But we do this with the same technology.
Yeah, AR could have a lot of like commercial applications for marketing, because they're doing a lot of you wave your phone in front of a product in the store shelf, and it gives you information. So if there was a more immersive kind of audio experience to go with whatever's on the QR code or whatever you scan, it could be quite interesting.
Exactly. And like directional audio, and you can think about this, if I'm sitting in front of I have some kind of device in front of me, a screen or so, looking into an augmented reality, and then you have physical devices around you, and you can actually create an illusion that there's a sound coming from that specific device. If you can track where the device is, and you have this dynamic HRTF technology, you can really position the sound so that it appears to be coming from that location. We actually did a little bit like that in a CES show a few years ago. We put up 2 studio monitors in front of people, and then we set the headphones on, and then we told them, you're going to be able to switch between the real speakers and the virtual speakers. And one of the journalists that were listening to that was like, guys, this doesn't work. You're just playing from the speakers. These headphones are quiet. And it's like, no, it's been on all the time. So it can be very convincing if you can track the objects and you can track the head movements with great resolution and smoothly update the filters in real time, actually.
Okay.
Yes,
so that's the key point about this head tracking thing is you update the filters in real time. What kind of filters are you talking about? Do you use...
We're using, for real-time application, if smoothness is the key, then we're using bicode filters typically, because it's faster and less memory and MIPS consuming.
Earlier on, you mentioned, generally the performance system for car audio, we use bicode filters rather than more complicated filters. What are more complicated filters?
Oh, we use FIR filters, and in many cases, and sometimes we do combinations of FIR and IIR filters to get sort of the maximum. With FIR filters, you have better control of detailed face characteristics, whereas IIR filters have other good aspects in terms of controlling the magnitude response, especially in the bass region, with higher accuracy without increasing the complexity of the filters. So we often combine these two filter types and various types of implementations also to save memory and MIPS.
Yep.
And then
go on. Yeah.
I was just going to say that also, and that's for the linear filters. And then when we come to speaker optimization in micro speakers, it's also a lot about dynamic and nonlinear processing to control the distortion of the sound and increase the loudness. So there we use also dynamic range compression and things like that, other structures.
Okay, so dynamic range compression is classified as a nonlinear filter.
Yep.
I want to ask something a little bit off topic, but take the case of an IIR filter, and you have essentially two historical samples of input, two historical samples of output. And from that, you can create a whole range of different effects, peaking filters, they call them, or high pass, low pass, shelf filters, and so on. I was trying to qualitatively understand how that's possible. Do you have any comment about that in terms of, let's say, what you're doing is you're looking at the gradient of the waveform at any moment in time, and based on that, how can you get it to be a whole range of different filters?
Yeah, it's true. I mean, that is what you're doing. You're really looking at the curvature of the whole of the waveform at that time. Yeah. And that's a good question. I was teaching those things back in the day. How do you explain it in a nice way? But from the top of my head now, I maybe can't come up with a good.
So you could say, for example, if the gradient is very high, that would be a high frequency. But that's not necessarily the truth. That's not necessarily the case, because it could be just a lower frequency at a higher amplitude. So I was trying to get an understanding of that.
But yeah, exactly. But you can also look at it in the frequency domain and in terms of poles and zeros. Because of course, it's some kind of averaging. If you just look at old samples, you can do one sort of averaging. But the thing is, you can look forward here, and that you get a feedback loop. That's the nice thing, right? Because
it's the feedback, isn't it?
It's the feedback that allows you to have much more finer control or detailed control. Yeah. And that's really the thing, because it's really like an analog feedback loop. It allows you to do stuff. It amplifies because it keeps on going. The feedback loop, and that's why it can become unstable as well, because you might be just adding and adding.
Yeah,
right?
Yeah. People that tends to be people with a traditional audio background think in terms of frequency responses all the time, but people in DSP always think in terms of impulse responses. Have any comment about what's the difference between the two?
So they are related. They are actually the same, you could say, because the frequency response is just the Fourier transform of the impulse response. They both characterize a linear system completely. Yeah. But also when I talk about impulse response correction, I I more mean that we look at the time domain properties, because we think that the ear and our human brains process sound a little bit differently. It processes sort of time frequency a little bit independent, or maybe not independently, but differently. So if we just look at the impulse response, what's in the tail of that impulse response of a speaker, for example, is not important in the time domain, whereas it adds up. That's often a late reverberation from a room, and that's not a big problem as we hear it. But in the frequency domain, it adds up some energy in the high frequencies. So actually, you need to look at them both at the same time. We talk about a stationary frequencies response, and then we can look at a short time window of the main pulse of the impulse response, and in the frequency domain, look at that. That looks very different. And all the details in the high frequency region has sort of gone away.
So that's an interesting point. So essentially, looking at a frequency response function, you lose the temporal information ultimately. Yeah. And so when you sit down to, say, take a frequency response of a speaker, and then just based on you can do magnitude and phase and modify it, you're actually missing some key information, which is what you just mentioned. That's fair to say.
Exactly.
And so the actual implementation of how a filter works, let's say a biquadratic filter, that's not the key point. It's what type of filter function you're ultimately trying to get to. And if you're just looking at a frequency response function, it may not be the correct one.
That's a very good point, actually. It's really it's not which filter type you use, it's really what the function is that it performs. And you can look at that both in the frequency domain and the time domain. And often you need to look at them in both domains, actually, to sort of fully understand what they're doing. That's an excellent point. It's very important. And that's why we tend to look at frequency domain information and smoothing it. And you also have to think about the fact that we're always measuring and listening in a space, not just in one point. So when you're listening or measuring in one point, you don't get also an accurate picture. So you need to have more points and see sort of a three-dimensional picture. It's also a spatial aspect to it, how these things vary. So there's all kinds of subtleties there, actually. And like you said, frequency domain, then you obliterate all the time domain information.
Yeah.
And of course, you need to consider both domains.
If you are designing, let's say, a magnitude-based filter of a frequency response, you want to end up with a flat line. So you essentially just take the inverse of that magnitude and try and make a filter that equals that. What are you doing with an impulse response to try and make it a perfect impulse? Is it because it's not just an inverse of the impulse response that you've obtained, is it?
Yeah, it's like a mirrored function, because this is a time domain convolution. So the filter becomes convolved in time domain with the impulse response. So there, you cannot look at them two as mirror images, but they are convolved with each other. So it is more complicated, but the idea is the same, that when you then filter the impulse response through your filter, what gets out there should be as close to an impulse response or perfect impulse as possible. And this is this convolution effect. So you're making a linear combination of the samples in your filter and in the impulse response, and that brings you the output of that. So it's harder to depict that in the time domain. You cannot see how those two add up like you can in the frequency domain. Okay. But if you take the time domain, the impulse response of your filter and the impulse response of the system, and look at them in the frequency domain, then they are the mirror inverse of each other.
Yeah. I got it. And so if you the length of your impulse response that you can operate on, that is limited by what? Is it the number of stages of filter? Is it?
Yes, well, you could say like this. To control the longer wavelengths, lower frequencies, you will need a longer FIR filter, higher order FIR filter. But essentially, it is the amount of the wavelength you can control depends on the length, the order of the filter. So the shorter the FIR filter, you would not be able to have any precision in the base response. And that's why we sometimes at IIR filters, because there we don't have that limitation. There you can be very precise in the bass.
Oh, I see. Okay.
So essentially, a higher degree of bass control requires higher filter orders, requires more DSP power.
Mm. And can an FIR filter actually do, let's say you have an impulse response, you have some reflection that arrives 100 milliseconds later. Is there an FIR filter that can actually do that, or is that only possible with an IIR filter?
If you had an echo at, say, 100 milliseconds after the main pulse,
yeah,
yet you can cancel that with an FIR filter, but it becomes infinitely long in the end.
Yeah, okay. So
it becomes an infinite an IIR filter. Yes.
Just carry on. Room correction is the same principle of trying to find a perfect impulse response. Try a filter that convolved with your impulse response gives a direct delta function.
Yeah, exactly. And then in reality, the direct delta function is an ideal. In reality, you should not try to invert, late reflections, for example, because we know it cannot be done simply. You need to have a robust correction that looks at various measurement points and looks at the common denominators of all these different points and make an impulse response that gets better on average and in each of these points. If you focus on trying to do too much, you end up making the impulse response in certain areas worse than in other areas. Right, it's important to have something that is robust. That's really key, I would say.
You mentioned mixed phase impulse, the term, or mixed phase impulse correction. What does that mean?
So we differ between minimum phase and mixed phase. So a minimum phase system or a minimum phase filter essentially only does a magnitude response correction. You can have non-minimum phase behavior in a room. It might be that you actually, or in a car, it might be that your center speaker, an obvious example is that your direct wave is actually lesser in magnitude than this reflected wave. Then it becomes a non-minimum phase system. A minimum phase correction of that will not be able to fix that. So you might have a flat magnitude response, but the impulse response actually got worse from your correction.
Right.
The mixed phase approach looks both at the minimum phase behavior and the non-minimum phase behavior, and so that's what we call mixed phase. It has both minimum phase and excess phase behaviors. So it has a look ahead buffer, so it introduces some latency, and that's how it can correct for those things, because otherwise you would need a non-causal filter to correct those things.
Yeah, and so your implementations are effectively a feed-forward system. Do you do anything with feedback?
No, not in room correction or in these kind of systems. We have, of course, played around with various kinds of feedback systems for, say, noise-dependent equalization of systems, so that you mask the noise continuously, by adjusting your EQ, and that's a feedback system. But for these type of applications here, no, we don't do any feedback. It's really feed forward systems that we employ.
Okay. And one more thing on the Bluetooth chip integration. So you had a list of different chips. What's involved in actually getting your code into those chips? That sounds like it must be extremely difficult.
Yeah, that can be quite involved, actually. One part is porting to a specific DSP, and some of them are fixed points, so you need to sort of translate your code to that. And you have to work with all the memory allocations and so on. The memory architectures are different on different devices. Sometimes it's the MIPS, sometimes it's the memories that is a bottleneck, and you have to make different trade-offs for that. So it can be quite challenging depending on the exact architecture, actually. So we have a lot of experts in the company that are really strong in this low-level programming, C-level and assembly-level programming. And then you need to integrate it as well with the rest of the functionality. So that's another major part of the work. That can be it can be quite a lot of work with that part, actually. So we think that, of course, more and more you see ARM chips becoming used in more and more areas, which is helpful because they are easier to work with, easier
Yes.
to upgrade and update and program for.
Yeah. So just imagine, so the chip will have its own base code firmware. Are you able to add on to that, or do you have to really work with their base code to actually get your functionality working?
Yes, well, both, I would say. It depends a bit from chip to chip, but we often, we add to an existing or integrate into an existing signal chain, you could say. So we made a sort of a generic porting for that particular chipset, and then we need to work also with integration onto the existing software that's on there.
So do the chip makers, let's say you had BES down there, do they license it off you and sell it to their customers, or do you license it directly to people who are buying BES chips?
We typically license directly to the customer, the hardware manufacturer, not to BES. That's the typical setup.
So does that, whoever that is, do they need to be quite highly skilled in working with the BES SDK themselves?
Good question. That depends, I would say, because we typically work with somebody who's a system integrator, and that might sometimes be the actual chip vendor, but also it could be an ODM, for example, and then we work with their integration teams. And normally not it depends on the company a bit, but normally not maybe the OEM.
Let me ask the question slightly differently. Let's say a headphone brand holder wants to implement this kind of technology. They would need to have a couple of other layers of support between you and them.
Yes, if they are, it depends a little bit on the company, but yeah, I would say typically we work through an ODM that's already working with the headphone brand customer. Yeah. That's the typical part. Some kind of system provider or system integrator that are already doing other things for them. So we typically talk directly with the brand, and then they direct us to their partner on integration. That's the typical case.
So let's say a lot of brands that are, to be fair, just try to be polite, is they're marketing focused. So
yes, so yeah,
they have no technical ability. They go to an ODM, and that factory says, we don't know anything about that. What do you do next?
Yeah, exactly.
Do contact you and say, hey, do you have a design house that can implement it? Or...
Yeah, but that is actually the case. We have some corporations with some of those typical ODMs that are already familiar with working with us, and then we can recommend somebody to that ODM and vice versa. Yeah. So it's often, not too difficult actually still. And you have some headphone brands on the other hand that are quite technical, more say the classical ones that have been in the industry for a long time and have built a legacy. And they do a lot of their work themselves also. So it's really kind of two different groups of headphone brands now. Like you said, some are more brand experience focused and have somebody that helps them build the stuff, and then we work with that partner.
Yeah. I'm spent.
I was like, Simon asking all these business structure questions sounds like he has a project in mind.
That sounds good, Simon.
I'm just curious. So, the point is, sounds like a lot of your business is the car industry, and they'll have fantastic technical capability. But in the more consumery stuff, a lot of the end brands, except for the big ones, don't really have a strong technical background. So True. They would have difficulty accessing your technology, essentially.
Well, I'd say the way a lot of those brands look at it, they need a partner for achieving their target sound, because they might not be so technical, but they turn to us because we are quite technical, and we can achieve the target sound that they want, and they don't have, they're only interested in getting the good sound. And they will still have somebody to build the headphone for them, obviously. Yeah. And then we work with them, and so far, that works quite well. They simply, we have this contact window, and then we talk with that person. There might be somebody in China, and we have team in China. So I would say actually that the brands that are not so technical themselves are often good partners, because we are technical enough to take care of the nitty-gritty parts together with their partner that builds the headphones for them or develops them.
Okay.
Excellent.
Yeah, so I mean, just trying to wrap up here. I'm realizing I'm talking and talking here.
Oh yeah, we've gone long. Call the affiliates.
But essentially, I'd say, with mobile phones, we work a lot with the small phones, the headphones, and so on. We're actually in hundreds of millions of smartphones. We worked with Oppo for many years and Xiaomi and so on. But when customers turn to us, talking about that, the brands and so on, they're not so technical. It's because we are reliable and the technologies are robust. They work in real life conditions. They've been tested, and really for any form factor and any target sound, it's that easy. And of course, what they turn to us for is also because they want to achieve a better, higher performance, and the algorithms that we have can help them do that. And then you have those brands that also want to have a consistent sound. To reach that across the different portfolios they have is one thing, and it applies to the different portfolios they have, different product categories. And for car manufacturers and system suppliers, it's also a lot about efficiency, saving time, and making sure that I always get the same result, and I don't end up in panic when it's time for launch.
Yeah.
So that's sort of that sums it up why customers work with us, I think. Plus the fact that we have this competence, I would say. So also when they want to develop a new concept, we're happy to work with them on new concepts and develop new stuff using the technology portfolio we have.
Okay.
And of course, just pointing out the obvious here, you can always contact us on this email address or on the web, of course.
Yeah, and we'll be sure to put the contact information down below in the description for everybody. And they can go to the website. He posted the URL, but it's all right here. And so, anybody's got any comments, questions, shoot it in the comments below. Or don't forget to subscribe and like and all that cheesy stuff for YouTube. It helps promote the content. It's pretty nerdy content, but that's okay. We like it. So Simon, do you have anything else to add?
No, that'll do for now.
All right. So Mathias Johansson from Stockholm with Dirac. Thank you so much for joining us. It's been a real treat. Learned a lot today about DSP and Dirac especially. So thank you very much.
Thanks, Dave. Thanks, Simon.
Okay. Bye-bye, everybody.
Bye.